So I hope you enjoyed that walk around of the two labs with Todd and Wendy. Now you have hopefully a pretty good idea of what the labs do, right? What happens to a soil sample as it goes through the lab. But you may be wondering why we made the labs the way we do. Why did we go through all the effort, hundreds of thousands of man-hours to create the Radicle Labs? Well, to answer that question, let's think about maybe an average American farmer. So in the eyes of the USDA, the average American farm is 464 acres. So imagine you have 464 acres, and for the first time, you want to get serious about nutrient management. And you know that in order to better manage your nutrients, to manage your inputs, you need to know more about your soil. So for the first time, you are going to collect some soil and send it to a lab. And it starts with planning your collection. Now, later today, you will hear more about soil collection from Mike and Eli. And you may already know that there are several different strategies to soil collection. You can plan a grid for your field, practice grid sampling, or if you know a little bit more about your soils, you can do something like zone sampling, or if you have several layers of data, you can create what we call smart zones and really be intelligent and strategic about where you collect that soil. But on our 464 acres, we don't know much about the soil yet, right? We're starting from square one. So we're going to go with 2.5 acre grids, a pretty common option here in the Midwest. So you go out to each 2.5 acre grid and you collect some soil. So you stick a soil probe in the ground to 6 inches in depth, and you pull up a core and you do that 8 times in that 2.5 acre zone. And then you take those cores and you put them in a bag and you number it number 1, and this is the start of your nutrient management journey. And you do that several times, right, across your property. In fact, if you add it up, you get 8 cores per sample location, 186 sample locations, and that actually adds up to 213 pounds of soil that you're removing from your fields. Another way to look at that is it's about 20 gallons worth of soil. But of course, you don't have them in 5-gallon buckets, you have them in those soil bags. Now they're numbered 1 through 168. And the next step is you put them in boxes and you send that 213 pounds of soil off to the lab. And so as a farmer, this is where your participation ends at this point, right? You would then wait for the results to come back. But as you're sitting there waiting for the UPS truck to arrive to pick up those boxes, you do start to wonder about what happens to that soil when it gets to a lab. And so the picture in your mind is something probably like off of television. You imagine maybe a bright, clean room. The soil comes in. There's a bunch of glassware in the room. Some of it has colored liquids in it. Some of the glassware has numbers on the side because of science. And there's somebody off on a counter putting drops of something into something else that spins. And then there's a machine over here that's printing out a report on your soils. And that report then gets to you and tells you everything you need to know about your soils. It gives you the perfect starting point for a nutrient management plan. So in reality, that's not exactly what happens, right? Most farmers have never seen the inside of a soil lab, or the outside for that matter. And most of us have never been to a soil lab. All we know is that we sent our 213 pounds of soil to the lab, and they're going to analyze all of that soil and send us back a report, right? Well, it's actually not even quite that clear, because what really happens in a lab is, even though you sent them 213 pounds, they analyze about 1 handful of that 213 pounds, less than 1 pound of soil. And that's maybe feels like a tangible amount of soil, like, okay, that's a that's a hardy quantity, a strong handful of your farm, but that's representing 464 acres, right? If we think about one sample location, each sample location is being represented by far less than 1 ounce of soil, which is pretty much exactly equivalent to a thimble full of soil. So if anybody remembers what a thimble looks like, I'm not much of a seamstress myself. But that's a pretty small quantity of soil to represent that sample area that you identified and you went out and collected 8 cores from. But just how small is this? Well, get out your calculators because we're just going to do the math pretty quickly here. So if we think about a thimble is about 4/1000 of a pound of soil. 2.5 acres, your chosen management zone, which is actually a fairly small area, has 5 million pounds of soil in it. So just quick math shows that that sample area then has about 1.1 billion thimbles full of soil. So if the lab is analyzing 1 thimble full of soil, well then that's about 1/100000th of your sample area. So that is what's being analyzed to give you that report that you're going to use to try to start your nutrient management plan. And so the question is can that really represent your field? Can a thimbleful really represent 2.5 acres? Well, the answer is actually yes, if we do 2 things well. The first thing that we need to do is thoughtful collection. And the second practice is true homogenization. So these are the 2 things we need to get that thimble to represent your sample area. So thoughtful collection goes back to planning your sample area. You'll hear more about this later today from Mike and Eli. But if you look at this map, these points were laid out on a grid, right? Regardless of known qualities about the field. We have a data layer, a soil type data layer on top of this map. So this is not thoughtful collection, where you're choosing your sample area regardless of the conditions of the field, regardless of characteristics you may know. Because we need each sample location, each sample area, to be a fairly uniform part of a field, because that is going to turn into a management zone. That's the report you get back is going to tell you a nutrient value for that zone. So we need to be able to manage it as a fairly uniform part of the field. The second is true homogenization. So true homogenization is a little bit more ambiguous, perhaps. Does anybody know what the word homogenization means? Or like what comes to mind when you hear that word? Something maybe like mixing, right? Mixing things together. So that's what most people think of, and mixing is part of homogenization, but that is not really telling the whole story. There's more to homogenization than just mixing. So let's illustrate this with an example. Imagine yourself you're not working in the field today. It's Sunday, and you're going to one of the annual events that you look forward to. You're going to your local farmer's potluck. And at this potluck, instead of looking for a relatively uniform part of a field and getting 8 soil cores, you're going to the relatively uniformly American buffet and getting 8 scoops of food. And so you walk away from this table at the potluck with a plate that looks like this. So there are 8 types of food on this plate. And you go and sit down, and then somebody walks up to you and says, hey, I'm going to need you to represent that with a teaspoon. Can you give me a representative teaspoon from your plate of food? And so you take the teaspoon and maybe you kind of start scraping little bits of food into it, but you realize you're not really going to get part of a roll onto the teaspoon very easily. And so you start mixing it together, and then you realize, this is just making a mess. I'm still not going to be able to represent it. So maybe you put it in something like a blender or a Ninja or a Vitamix, something to turn it into something else, kind of a smoothie of sorts. And then you take a spoon of that and you still wonder, it's like, well, how do I know that I have representative parts roll and spaghetti and salad all in this 1 teaspoon? It's really hard to know that it's homogenized just because you mixed it together. But maybe this is an unfair example. You think, you know, this table is not a uniform part of a field. You know, there's too much variation there, so it's not fair to try to create a representative sample in a teaspoon. So instead, think about the dessert table. After you finish your chicken smoothie, you go over and grab an Oreo milkshake. And then somebody asks you, hey, can you give me a representative teaspoon of that? Now, we have a lot better odds here, right? We've got the most, maybe 3 ingredients here that we're looking at. And it's already mixed together, so it seems fairly ideal. But even still, if you've ever had an Oreo milkshake, at least the ones I've had, it seems like you stick a spoon in it and pull it out, and somehow you're likely to get vanilla ice cream or half of an Oreo cookie. It just seems to work that way. So you see, just because things are mixed together doesn't mean they're homogenized. True homogenization is more difficult. And this is not just a problem at potlucks. Soil labs face this problem every day because they mix soil when they get it using something like this. This is a hammer mill similar to or identical to what some soil labs use. We use this here for grinding dry soil. And the other day I took some soil and I actually put some color dye in it. And so this is some soil that I dyed yellow and ran through the hammer mill. This is some soil that I dyed blue and ran through the hammer mill. And it did a good job of pulverizing the soil. But like we just highlighted, when we pull soil out of a field, there's variety in the soil. So what happens if we just had soil that was half blue, half yellow? So that's the minimum amount of variety, right? You're just looking at 2 fractions of the soil. Well, I did that. I actually took blue and yellow soil cores and ran them through this hammer mill, and this came out. If you can see this, it's pulverized, but it's just blue and yellow fragments. You can still see the 2 colors, right? This is mixed, but it's not homogenized. By comparison, if I take some blue and yellow putty and I start kneading these 2 things together, what do you think is going to happen? Any guesses? What do you think I'm going to get out of this blue and yellow putty when I knead it together? Green, exactly. So when I get this to be green putty, the beauty of that is that then I can remove any part of it and it's green. It won't be blue or yellow or some random combination of blue and yellow. It will be green. So if you can see that, I'm not quite done kneading it yet, but that is homogenization. Not a mixture of blue and yellow, but a new green combination. And so that is what we're looking for. Instead of just a random spoonful of an Oreo milkshake, we're looking for that perfect bite, because that only comes with true homogenization. So Radicle, the whole Radicle platform, is designed to address these 2 requirements to get that thimble of soil to represent your sample area. And how do we do that? Well, let's think back to the first point, so thoughtful collection. The Radicle platform has both software and hardware tools to do this. The American author Napoleon Hill coined the phrase, plan your work and work your plan. This is easier to apply to soil sampling because of Radicle. With the GeoPress and the Radicle app, we've made thoughtful collection easier than ever. And that is really important because that's what sets the Radicle Labs, what you just toured earlier, up for success. Radicle Labs ensure true homogenization. And they do this simply by design. Where homogenization is nearly impossible in a traditional soil lab, it's actually pretty easy with the Radicle Lab. So let's take a closer look at exactly how we've done that. And some of these things you'll recognize from your walk around with Todd and Wendy. So we start by loading the whole geotube into the Radicle Lab. So the whole sample you collected from your zone, 2.5 acre grid, whatever your sample area is, all of that soil is loaded into the lab. And the first thing that it goes into is a wet grinder. So notice I said wet grinder, so we mix the soil, grind the soil with water. Where in a traditional lab, soils are dried and then ground dried, which makes them very difficult to homogenize. With water, we're able to take all the nutrients and all the minerals and just the particles of the soil and get them into a mixture, into a slurry, into solution. And after we do that, we start taking measurements. You'll hear more from Brad about this later, but there are a lot of assumptions that have to be made in a traditional soil lab just for the sake of throughput. Well, we don't like making assumptions, so we take measurements. We measure the mass of the sample, the volume of the sample, the mineral density of the sample, and that allows us to prepare it for chemistry because we don't want to make any assumptions. We want repeatable, precise results. So after we're done homogenizing the sample, measuring the sample, we then send it to the other side of the lab for analysis. As we do this, we continue to homogenize the sample because we don't want there to be any opportunity for anything but true homogenization. So this has all been about the physical processing of the sample. We're not talking about any chemical results yet. This is all physical processing. But we've also made innovations on the chemical analysis as well. And you saw some of this a minute ago, and you'll hear more about it later. But the first big leap forward that we made was the creation of a product called MicroFlow. So MicroFlow is essentially a series of pumps and valves that allow us to really precisely handle water, chemicals, analytical chemicals, and soil, and mix these together and filter them very quickly, very precisely, very repeatably. And what this has done is this has taken many, perhaps to a certain extent, dozens of manual steps from a soil lab and turned them into one automated process. So we have a chemistry team here. You will actually meet them later. And they say that even though they are great chemists, this performs soil analysis far better than any human ever could, including them, and they're very good. We did not stop here, though. So MicroFlow was what got us our first results for farmers, but we wanted to go further, continue to get more value out of the soil test. And so we developed a technology called MicroGlow to add to MicroFlow. MicroGlow works on a different principle. So with MicroGlow, we are literally incinerating part of the soil sample into a plasma arc. So Gabe here is a member of our chemistry team, and he's going to demonstrate part of why we are doing this. why we are sending this soil sample into a plasma arc. But know that fundamentally when soil enters the plasma, some of the ions in the soil get excited. So there are many ions in soil. Some of these we care about on a soil test. We want to measure the levels of some of these ions, cations especially. And when they enter the plasma, these ions get excited. Think of it like getting a shot of caffeine. So they enter an energetic state, but they quickly relax. They fall back down to a grounded state. And when they relax, they release some of that energy in the form of light. And some of that light we can see. Some of it we cannot see with our eyes. But if you look at this plasma arc, you can see some of the colors coming out of that plasma. So there's a lot going on there. It's hard for our eyes to detect just how much is coming out. But Gabe is going to show here how if we simplify it to just single elements, our eyes can differentiate between elements. So he's going to ignite some alcohol solutions. And you can see those solutions burning with different flame colors. The one closest to me is strictly alcohol. And then the next three have elements added to them. And the colors are all different. The one on the very end, furthest from me, you actually might have noticed changed colors. And that's because there's actually two different elements in that one, and so there are two flame colors burning. Our eyes struggle to differentiate between those, and so we tend to see one color or the other color. But this is illustrating that different ions, different elements, have different wavelengths of light that are emitted. So with MicroGlow, we are able to tap into more of the contents of the soil to provide more value. So again, think of the periodic table. Many of these elements are ions in the soil. And so we are able to measure some of these now that we have MicroGlow, energizing some of those ions. And then as they relax, we capture the light that's being emitted from them. And if you're wondering, the labs currently measure pH, buffer pH, phosphorus, potassium, magnesium, calcium, and then we calculate the cation exchange capacity. And it's only because of these technologies that we've developed that we've been able to merge this with the Radicle Lab, so that thimbleful of soil can accurately represent your sample area, and we can provide these results to you. So let's think back to how we compare to a traditional lab, how the Radicle Lab compares. So the Radicle Lab analyzes moist soil. It processes moist soil to get true homogenization and give you more accurate results. You'll hear actually more of the issues with drying soil from Brad later today. We also homogenize the soil as a liquid instead of trying to use something like a scoop to approximate it. We take measurements of the soil instead of making assumptions. We've automated the chemistry process. We've automated the extraction of the nutrients out of the soil for analysis. And we rapidly filter the soil. This is something that Brad also will talk more about, because this is unfortunately a huge source of variability in a traditional lab. And we've removed that even from consideration. We barely talked about it here today. And the labs automatically check themselves. Pretty much every component on the lab is evaluating itself every time a sample runs through to ensure that you're given the correct results every time. And then we continue to grow this technology. You know, if you take away one thing here today, I hope that it is that we are putting a lot of effort into always trying to bring better information, offer better tools, bring better data to the farmer and to the agronomist. And we are still on that journey. We are not done yet. And this is in an industry where we use a lot of, I'll just generously say, vintage data to try to make our nutrient management decisions. So it's one thing to talk about repeatability and reliability, but it's another to prove that we are better. And for that, I'm actually going to hand it over to Wendy.
Thank you, Reid. All right, so let's put some numbers to this, right? We can talk about the theory, we can talk about the process, the how, all day long, but what effect is it actually having on our lab results? So I want to start by telling you guys about a study I did when I was an intern here in 2019. I interned for the R&D agronomy team, and I got to do this really cool soil study. So I went out to one of our fields here, collected a soil, and brought it back to the shop, mixed it up in that plastic tote that you can see there, blended it all together really well so I had one uniform soil sample. I parsed it out into a whole bunch of different bags, and then we stored those bags at different temperatures. So we stored it at a warm temperature, a cool temperature, and just like a normal shop temperature. And then we shipped these out over 14 different days to one of the laboratories. And I was super excited to get this data back. I was like, okay, we're gonna see all sorts of trends between temperature and time and how that affects lab results. And we got the data back, and what I found was that it's unpredictable, that it's unreliable, that it's not consistent. So, for example, here is potassium. So you can see all three different temperature ranges, and you have day 2, day 4, day 7, and day 14, but day 7 just doesn't really make sense in the data set. I don't know what happened on that day, but I have a 50 part per million swing there, right? So as I started getting this data back and looking at these and trying to find patterns in it, I realized how much variability we are seeing in the data that was coming back from the lab. So to add it all up, we had a total of plus or minus 10% variation with phosphorus and plus or minus 30% variation in potassium. Now when you put actual application numbers to that, we're looking at about 40 pounds of DAP and 134 pounds of potash. That's per acre. Now start adding that up a bit across your farm, and I don't know about you, but that starts to look a little scary, right? However, at this point, all I had was, okay, this isn't very reliable. This starts to add up and make a little bit of sense of why we don't always trust lab values. And now, after understanding more about how the commercial lab works, understanding some of the stuff that Reid talked about, the wet versus dry soil testing, weighing the sample versus doing a 2-gram scoop, I started to understand why we see some of this variability in commercial labs, but at the time back in 2019, we didn't have anything else to compare it to. We didn't have any better options, right? So I'm excited to tell you guys that we did this study again this spring. So we went out and collected soil from 6 different locations. So we got 6 5-gallon buckets across 6 different soil types. And we brought those buckets back to the shop, and to blend each soil type up, because this 30 gallons was too much to hand mix, we actually had to go out and get a concrete mixer in order to blend that up pretty well. So after a little bit of work there, they got that all mixed up, all uniformly mixed together, so we had one sample. And then we split that out into sample size bags. We vacuum sealed them and froze them. You'll get to see some of that storage later this afternoon when you do the tour. So that they are all being stored in a stable environment. Okay, so then we started shipping these samples off to 3 different labs. Each time we shipped the samples off, we would send 3 of each soil type at a time, okay, so that we had triplicates to check against. And we'd send it about every 2 to 3 weeks, and then we also ran it through the Radicle Lab. So, did we do a better job? So you can see Radicle Lab, Lab A, Lab B, Lab C. Each of the yellow bars are the replications that we sent, so we've sent it off about 5 different times, once again about 2 to 3 weeks apart. And then the white lines that you see are the amount of deviation within the 3 samples that we sent each time, okay? So this is just one of the soil types, and so I want to point out a couple things. First of all, look at the consistency of the Radicle Lab there, and then look at the difference between replication 1 and replication 3 on Lab A. That's like 50 part per million swing, right? Just about a month apart. And then also like on Lab C there, on 4 and 5, that white bar being really large means we had a lot of error, a lot of deviation between those 3 samples that we sent to the lab all on the same day, all in the same soil type. Okay, another soil type that we sent in, once again, Lab A struggled between not week 1, but replication 1 and replication 3. We saw kind of a swing there. Look at Lab C, Rep 1. Wow, that's a lot of variation. Keep in mind, when you guys are sending in soil samples in, when we go out and pull a soil sample, we're only pulling 1 per sample location, right? Nobody goes out, unless you're doing a study, and pulls 3 replications in each spot, sends them to the soil lab, and then averages them together to get a more accurate sample. We're just doing 1 at a time. And depending on which one you happen to get there, this is why sometimes we get our soil test results back and things just don't make sense, because there's a known amount of variability, a known amount of inconsistency in our lab results. One other thing I want to point out here, I think it's a little bit better shown back on this first one. Another thing that might stick out to you guys is that, whoops, this was ahead, let me back up. Our potassium levels do display a little bit lower in these graphs. Like if I was to average these numbers together, we're really consistent, but we're also a little bit lower. So I know that might be a little disconcerting, but one of the reasons with potassium in particular is that we're doing that moist analysis, and when you dry a soil test before analysis, if you have a low-performing soil, drying it increases the soil test value, and if you have a high-performing soil, drying it decreases the value. So we actually show a little bit better clarity, a little bit more range, because we're not drying that soil sample. So that's what we're seeing there for that difference. Okay, phosphorus. So once again, really consistent on the Radicle Lab. Lab B and Lab C both have a couple replications there that once again have a very large deviation in one of the replications. And one more graph for you guys. Here's another soil type again. From replication 1 to replication 3, 4, and 5 on Lab C. Like, it's just not consistent. It's just not predictable or I can't trust the results I'm getting back from this. So, however, I'm excited to say that the data we got back from the Radicle Lab is consistent, is predictable and reliable. And unlike the study I did back in 2019, now I do have a better option. Now I do have a more consistent option to use. And I did this across 6 different soil types. I could keep showing you guys graphs all day long, and they look similar to this. So, thanks for joining us today, learning a little bit more about the Radicle Lab. That's all we've got for you in this session. If you have any questions, you can grab us, but I think we should be rotating in the next couple minutes, and you'll get to learn a little bit more about some of the processes with Brad that the Radicle Lab is going through, as well as the crop response data and the crop response trials that we're working on. Thank you all.